Our project is about modeling population of Adelie and Chinstrap penguin on Signy Island. So we use Lotka-Volterra model. The Lotka-Volterra model is usually used to describe the interaction between two or more species in the population over ecological time. For this project, we decided to model a Lotka-Volterra system, which to be specific, the Lotka-Volterra competition model. We choose Chinstrap and Adelie penguin as the two competitive species. Alejandro et al. In their article state that these two species compete for available space for breeding areas since they breed at same sites. We modeled a Lotka-Volterra system to find out the effect of Chinstrap penguins on the population of Adelie penguins. The data that we used are the population size and breeding success of Adelie and Chinstrap penguins on Signy Island from 1978 to 2020 that can be found at Ramadan Data Repository website. This is the general equation of Lotka-Volterra model with the explanation for each of the variables. Since the general equation before this does not fit our situation in modeling the population for both Chinstrap and Adelie on Signy Island, we modified the general equation and get this equation. Basically, the variable is the same, but there is additional sigma variable. The rest of the coefficient is calculated using our data.
Alpha is the correlation between the total number of Chinstrap pairs and the total number of Adelie fledgling. Beta is the correlation between the total number of Adelie pairs and the total number of Chinstrap fledgling.
Sigma is the total number of Chinstrap fledgling divided by the total population. K1 is the average of the total population of Adelie, and K2 is the average of the total population of Chinstrap.
Next, moving on to the methodology. Firstly, we need to find the equilibrium points. For this system, we get a total of 4 equilibrium points, which are 0, 0, 0, 3, 3.60, and 2.1944, 1.9072. Since both of our modified equations are nonlinear, we linearize them using the Jacobian matrix method, and from the formula, this is what we get. After that, we check out the stability of the system considering all the equilibrium states. Firstly, by substituting all the coefficient values at the fixed points of 0, 0, the Jacobian matrix that we obtain is 0.146, 0, 0, 0.127. After some assumption and changes, we get the linear differential equations in terms of y1 and y2 and transform them into the matrix form. We get the eigenvalues and also the eigenvector, which provide us with two general solutions for this system. Next, by substituting the initial values that we get from the data, we get the value of C1 and also C2. Therefore, the specialized solutions for this system are y1t is equal to 1873 exponent 0.146t. And y2t is equal to 1791 exponent 0.127t. Next, we have to determine the singular point and the stability of the system. So, we calculate the determinant of the matrix, which show us that the value are larger than 0. So, we calculate the trace of the matrix as well. It can be observed that the determinant of the matrix is larger than 0 but smaller than 1/4 times the trace of the matrix to the power of 2. Thus, its singular point is known. However, since both of the eigenvalues are positive, the system is unstable at the equilibrium point of 0, 0.
Next, we have fixed point of 0, 3. The Jacobian matrix obtained is as shown. The linear differential equation that we have is y.1 equal to 0.146y1 and y.2 equal to negative 0.063246y1 minus 0.127y2. We have transformed the equation into a matrix, and the eigenvalues obtained are lambda 1 equal to 0.146 and lambda 2 equal to negative 0.127. The eigenvectors for lambda 1 is negative 4.3165 and the eigenvector for lambda 2 is 0, 1. We have obtained the general solution, and we have substituted the data from initial value, which is y10 equal to 1873 and y2 equal to 1791. Thus, we have the specialized solutions are y1t equal to 1873.02 e to the power of 0.146t and y2t equal to negative 433.92 e to the power of 0.146t plus 2224.92 e to the power of negative 0.127t. Next, we must determine the singular point and the stability of the system. To identify the singular point, we can find the determinant of the matrix, which is negative 0.018542. It can be observed that determinant A is less than 0, so it is a saddle point. However, since both eigenvalues are different sign, the system is unstable at the equilibrium point of 0,3.
Right, so next we will substitute the coefficient values at the fixed point of 3.60, which is, and we can obtain a Jacobian matrix in the form of 4x4. And then we can also construct a linear differential equation based on a matrix. And then we, based on certain assumption, which is x dot equals to y dot 1, x equals to y1, y dot equals to y dot 2, and y equals to y2. We can transform it to form a set of equation, and also transform the MDE to the form of a matrix. Alright, so then we calculate the values of eigenvalues, which is lambda 1 equals 0.146 and lambda 2 equals 0.051. And then we also calculate eigenvectors to get the general solutions. So from the data, the initial values are values of x0 is equals to y10 equals to, which is equals to 1873, and y0 equals to y20 equals to 1791. Based on both of these values, we find the value for C1 and C2. Alright, so then we can obtain the specialized solutions equations, and then after that we determine the singular. We want to determine the singular point and the stability of the system. So to identify the singular point, we need to find the determinant of the matrix first, which we obtain the value of 0.0074606. And then as we can see that the determinant value is more than 0, we need to find the trace of the matrix as well. Okay, first we find the trace value of the trace, which is 0.1971, and then we calculate the value of the square of trace A over 4, which is equals to 0.009712. This is because we wanted to compare these values with each other. So we can observe that the value of determinant A is more than 0 but less than the value of the square of trace A over 4. Hence, based on this, we can make conclusion that its singular point is not. However, since both of the eigenvalues are positive, the system is unstable at the equilibrium point of 3.60.
Lastly, substitute equilibrium point of 2.1944, 1.9072, and we get Jacobian matrix as followed, and then we get the linear differential equation, and then we assume that x equals to y1 and y equals to y2, and then we transform it into matrix, and then we find the eigenvalue, which is negative 0.0333 and negative 0.136, and then we get the eigenvectors as followed, and then we find the general solution. Okay, from the data, we have the initial value of y1 at time 0 and y2 at time 0. So with the values, we get the values for C2 and C1, which is C2 2151.4057 and negative for C1 is negative 278.4057, and therefore the specialized solution are as followed. Next, we have to determine the singular point and the stability of the system. So we have to find the determinant of the matrix, and we get the value is negative 0.0454518, and then we get the determinant of A are larger than 0, so we have to find trace of A. After we get the trace of A, we have to square root it and times it with 104, and we get 0.0071995, and you can observe that the singular point is not, and the system are stable at the equilibrium point of 2.1944, 1.9072, since both of the eigenvalues are negative. So that's all from us. Thank you.